lads and ladies, welcome back. Sorry, Zoom's telling me that my microphone is not working, but it's also telling me that my microphone is working. Yeah, I think this is working just fine. Okay, so today we're going to do a few things. We're going to talk about the first test, which is getting close. We're going to finish section 2.7, which is on combinations of functions. We kind of touched on it a teeny bit, but we really haven't worked it yet. And if there's time, we may introduce a little bit of section 2.8, but probably not going to get there. So let's get in here and do the thing. This is MAC1140, section 009, which is a pre-calculus class. And today is the 16th of September, 2021. On the docket, we're going to talk about exam 1. And then we're going to finish section 2.7 on combining functions. I think I mentioned last time that mathematicians, not necessarily my flavor of mathematician, but mathematicians called algebraists, are really into like classifying objects, and one of the sets of objects they like to try and classify are functions. And one of the tools for doing that is starting to treat them as algebraic objects in their own right. So like studying what happens when you add two functions, multiply two functions, that sort of shit. There is another operation that you can do besides the sort of natural, obvious algebra operations, and that's the one that algebraists get really excited over. But before we get into any of that, I want to talk about exam 1. So I have set the date for exam 1. I ran a poll in one of my other MAC1140 classes that shares the same dates as yours. And they voted overwhelmingly for one of the two dates, so I'll go ahead and tell you exactly what options I gave them, and not to frustrate you if this isn't what you wanted, but just for transparency's sake. So we're going to finish 2.7 today, we're going to finish 2.8 on Tuesday of next week, and we're going to have exam 1 on Thursday of next week. So exam 1 is 1 week from today. The options I gave them were the 23rd or the 28th. With the caveat that if we go with the 28th, that'll give you a little bit more time to study between finishing the material. But this day would then be a lecture on totally different material that you're not being tested on the 28th. And also it's going to soak up a little bit of prep time that we could have used for one of the harder tests down the road. So doing the test on the 23rd puts us right back on schedule, the time that we lost from the holidays, and also I think is the most efficient for you guys. So exam 1 is 9/23, which is next Thursday, exactly 1 week from today. And it's going to cover everything that we will have talked about up through that prior Tuesday. So it's going to cover 1.1 through 2.8. What else is there? There's something else, wasn't there? WebAssign stuff we can take a look at just so you know what's coming, what to expect. So you guys have, here are you guys. So you guys have homework 6 up right now, and rather than having that be due today, I set that to be due on Monday of next week, because the 2.7 stuff I knew we weren't going to get to talk about it as much as we'd like to on Tuesday. There will be another homework I'm going to release today, homework 7, which is going to be the remainder of section 2.7. It's going to be a short one, so over the weekend you'll want to make sure you knock out any of homework 6 that you haven't done yet, and also homework 7 that will be published later today. And before the test, there will be one more homework. So again, the test is going to be next Thursday. Next Tuesday, I will release a 2.8 homework set, a short one, but a 2.8 homework set, and you'll want to work that before the test. The best things you can do to study for the test is to go back through the homework problems. So WebAssign, in addition to like going back through and saying practice another, there's something called the personal study plan in WebAssign, and I really encourage you to play around with that. So to study, first, do the homework. homework and the quiz. But then also check out the personal study plan in WebAssign. This is an AI-assisted feature that the Cengage reps have been pushing for a long time. I've looked at demos of it in the past, and I didn't like it until last year when I finally saw a demo that looked like it was actually doing what it should do. So if you hunt around in WebAssign for something called a personal study plan, you will see it should populate an assignment with questions of the type that you got wrong a few times as you worked through the homework. So like, maybe some of the problems in there, the first time you attempted it, you nailed it, got it right. It's not going to bug you about those. But if there's one that you got wrong 2 or 3 times before getting it right, it will give you a couple of those sort of problems to practice on. So it's actually a really intelligent system. It's a really good way to go back and fill in gaps from previous assignments that were, maybe persisted a little bit beyond the homework. It was requested that I put together some sort of exam review. As a general rule, I'm not big on practice tests. I don't think they are wise. But I am going to try to put together something for you. So I want it to be a low stakes problem set. I don't want it to be something that you have to worry about for a grade. So if you don't want to do it, you don't have to do it. It'll probably be in Canvas. I'll find some way to post like a worksheet or something in Canvas that you guys can treat as a review for the test. But my personal advice for you is to make sure you have mastered the homework and quiz problems, because I'll be drawing from that sort of material for the test. And then the emphasis here is to draw your own graphs. I've been saying that, pretty much each one of these homework sets, draw the damn thing yourself, right? Don't just click around until you find the right one. This is probably the most important. So make sure you do the homeworks, quiz. I'm going to release another quiz. And check out the personal study plan if you feel like you want more practice after that, or look into Canvas. I don't know how long it's going to take me to put together the review type worksheet thing, but I'll do my best to get something out this weekend for you. To take the test, you have 2 options. You can take the test in the testing center, which is on the Northwest campus in Building N. If you want to do that, you need to contact me. Canvas message, please. You still have to take it on that day. You still have to take it on the 23rd, but I'll have a window like class time plus or minus 2 hours where you can take it, and that will get you around having to deal with any of the proctoring stuff. So if you want to avoid using Honor Lock, and I'm also going to require Zoom, then you can take the test in the testing center. The other option is online. For this, you're going to need Zoom on your phone, and Honor Lock in Chrome. So if you don't like the Chrome browser, I understand. I don't like it, but if you're going to take the test online, then you have to use Chrome, because Honor Lock is a Chrome extension, so make sure you have Chrome installed. Then update Honor Lock. Por favor, don't, if you've got if you had to use Honor Lock 2 semesters ago and you haven't used it since then or something like that, please uninstall and reinstall the extension, or check and see if there's an option for updates, because they updated Honor Lock at least twice over the summer, and if you have an old version installed, it might not work. The other thing you're going to need is Zoom installed on your cell phone, because the way I do online testing is a little bit different than the way some professors do. You're going to sign into a Zoom meeting on your phone, and then before you launch the test, you're going to have to get the okay from me about how your phone is set up. Your phone is going to be set up somewhere like over here, off to the side, or off, somewhere I can see the desk, the paper you're writing on, your hands, and your lap. I need to be able to see all of those things on Zoom on your phone if you're going to take the test online. I know that's a bit of a hassle, but that's the way it works. So if you're gonna take the test online, you're gonna sign into class that day like normal, only you're gonna do it from your phone. I know probably some of you are doing that anyway, but you're gonna do that from your phone. You will set up your phone so I can see your desk, your hands, your lap, your paper. And then once I give you the thumbs up in Zoom, you can launch Honor Lock in Canvas and take the test there. I know this is a hassle, I get it, but cheating has been a fucking problem for me the last couple of years. I think it's been a big problem for everybody in higher education, and this is the best thing I've done to combat that. So you can take it in the testing center if you don't want to deal with any of that hassle, or you can take it online during regular class time, but you're going to have to use Zoom on your phone and Honor Lock on your computer. The test is going to be in Canvas. I can show you the format of my exams. The questions obviously will be very different from this, but this is a differential equations test from the summer. Here's what they're going to look like. All right. There will be, this takes a minute to render. There will be a handful of true-false questions like these. Obviously different questions, but true-false questions. Each will be worth 4 points. There will be some multiple choice questions like these, 4 options. Each one will be worth 6 points. And then the remainder of the test will be free response questions like these, each one worth 10 points. For the true, false, and multiple choice, you just click the answer you think is correct and move on. I do recommend being a little bit careful. My true, false have a reputation for being somewhat tricky. And you either get them wrong or you get them right. If you get them wrong, you don't get any points. If you get them right, you get all the points. For the free response questions, the way it works is, there will be a problem here. In this box, you will type your final answer and just your final answer. And then on your own paper, you will write out all of your steps. You're going to show work like you would on a paper test in class. After you finish the test, but before you sign out of Zoom, you will scan the written work and submit it to a separate assignment in Canvas. And then the way I grade these, the free response problems are out of 10 points. Having the correct answer typed here, 2 points, right? Just the answer ain't worth shit. What I need is your work. And then the work, the actual procedure, step by step, that's worth 8 of the 10 points. If you do all the work right and then miss a minus sign or something like that, you'll lose a half point or so. So I'm happy to give partial credit. Most of the credit on the free response problems is partial credit of one flavor or another. I'll say one last thing. The final answer that you type in this box has to match the shit on your paper. All right? This is critical and obvious for cheaty reasons. The answer you type in this box, and the only thing you type in this box is your final answer, has to match the result from the stuff you get on your paper. If they don't match, or if you don't type an answer at all in this box, even if your work on the paper is perfect, 0 points. All right? So gotta type the final answer in the box during the test, gotta show your work on the paper, and then scan it after the test, and they have to match. That's the procedure, those are the rules. Are there any questions about this? Okay, let me remind you briefly. So the content of the test is 1.1 through 2.8. That's last section is one-to-one functions and their inverses. Today we're finishing 2.7. The thing I want to remind you though is this. I'm not the youngest dude in the world. I'm not the oldest. I'm not the most square dude in the world, and I'm not the most loose. But I have gotten real fucking good at catching cheating over this last year and a half. I have fried 20, 30 people for cheating over the last year. My record is 9 on one test. I want to remind you, if you feel any temptation to do something sketchy on this test, instead of doing that, just reach out to me, all right? I'll give you some extra time. I'll give you some time to prepare, right? Somebody's going to be sick. Somebody's going to have a car accident the night before. There will be a makeup test. There always is, right? Because there's always somebody, at least one person who needs it. if you're in that position where you're about to do something that would get you in trouble if you get caught, instead of doing that, just say, hey, can I have a little bit more time to prepare for the test? I'm in over my head, blah, blah, blah. And I'll give you that time, and I'll give you some extra office hours. I'll do whatever I can to help, but please, 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 please don't cheat, all right? If you do, I will catch you, and when I catch you, I will be mean about it. That's correct, Suzanne. Yeah, so the test is in Canvas, not on WebAssign. The test will look just like this. The questions I'm going to ask you are going to be very, very similar to the homework questions. Let's see, I think that's it. Yeah, I think that's everything I wanted to say. Oh, yeah, one other thing. People looking for extra places to study. One last thing that is really useful. Add it in here if I can. 3. Look at the chapter review and test in the book. So people often come to me after the first test and say, that true-false was really hard, and I didn't, I wasn't expecting it to be that hard, and is there anything I can do to study for the true-false on a future test? And yeah, absolutely. The textbook has really good true-false and multiple choice questions that you can use to prep. So if you're not using the ebook in WebAssign, I get it, like it's a little awkward, but at least look at the Chapter 1 and Chapter 2 review questions in there if you're nervous about that. It's a good place to get a feel for the style of question I'm going to ask on the test. All right. The homework questions are, of course, questions from the book, right? The homework questions in WebAssign are taken straight from the textbook, so they are also very much of the type I will ask on the test. Okay, I think that's everything about the exam. Any other questions?
So we just use like our phone to scan our scratch work and then submit it on Canvas.
That's correct, yeah. So if you look in Canvas, I think I've created all the assignments for you guys' course here. If you look in the assignment section on Canvas, you will see like exam 1, take the test here. So you'll go here to take the test, and then after you finish the test, but before you exit Zoom, you will use your phone to scan the work, and then you'll submit the scanned work here. Apps that are good for this, I've been using Cam Scanner for a long time. I like it. I get a free, like, fancy Cam Scanner account because I'm a teacher. I don't know if the free accounts for students are as good. I've heard people say that the free account has like a limited number of scans, but software that works well for that, if you have an iPhone, the Notes app works really well. If you have an Android, Cam Scanner is nice, but I've heard that they're starting to make it cost money and restrict the free accounts. Somebody mentioned to me that Adobe has a scan app for both Android and iPhone that's supposed to be really good. So play with one of these. Cam Scanner has worked really well for me. This is apparently working well for some people. And if you have an iPhone, the Notes app I hear people use a lot, but it does need to be scanned using a scanning app. It needs to be in PDF. Any other questions? Obviously, if you have a physical scanner, you can use that too. You don't have to use your phone, but I think more of us have phones than scanners. All right, let's get into the material then. So today we're going to finish section 2.7, which we barely started. This is on combining functions. The basic idea is this. Given two functions, f and g, with domains, I'll call them dom f and dom g. So these are both sets, right? The domain of f is dom f, domain of g is dom g. Given two functions, f and g, we can form new functions. So what we're doing here is defining an algebra operation on the space of functions. And the first few are kind of really silly, or not silly, but a little obvious. So I can form a new function and call it f plus g. I can form a new function and call it f minus g. I can form a new function and call it f times g. I you can form a new function and call it f over g. And the definition for each of these is precisely what you would think. F plus g of x is calculated by finding f of x and adding it to g of x. This is called pointwise addition. I'm going to define this new function f plus g as the point-for-point sum of the outputs from f and the output from g. And the others are all defined analogously. F minus g of x is f of x minus g of x, pointwise differences. F times g of x is the pointwise product, f of x times g of x, and f over g evaluated at x would be f of x over g of x. These are kind of obvious, right? This is like normal algebra we do with numbers, just going to do it with functions. I can add two numbers, I can add two functions. Multiply two numbers, multiply two functions. There's something you can do with functions that you can't do with numbers, and that is to form a composite. So this is f circ g. This middle symbol here is read as circ, or sometimes just the word of, because it's defined by saying f circ g, or f of g of x, is what you get by taking f and then plugging g of x into it. And this last guy again, his name is a composite function. C-O-M-P-O-S-I-T-E, composite. We are composing the two functions. And the little operator here is usually read as circ, C-I-R-C, short for circle, or just the word of. You can read this as f of g. The domains of some of these are quite obvious. The domains of some of these are a tiny bit less obvious, and then like way less obvious. So let's start up here. If I want to plug a number x into this function, f plus g, like suppose I want to plug in 2. F plus g of 2 would be f of 2 plus g of 2. So what needs to be true about the number 2 in order for me to plug it into this function? Thinking of domains. I know it's an open-ended question, but please genuinely think about it. If I'm going to plug a number like 2 in here, what needs to be true about the number 2 with respect to the domains of f and g? Let me say that slightly differently. All right? If 2 is in the domain of f, but 2 is not in the domain of g, can I plug it in here? Can I plug 2 in here if 2 is in the domain of f but not in the domain of g? No. Yeah, exactly. Yeah, Suzanne's correct. So in order for me to plug 2 in here, it would have to be in the domain of f and in the domain of g. In other words, the set of all numbers I can plug into this function is the set of numbers I can plug into f and g. The term for that is the intersection, and that's the domain of each of these. Just the first 3. So the domain here is the domain of f intersected with the domain of g. In other words, the stuff that's common to both, right? Like if this is the domain of f and this is the domain of g, then this is that intersection. It's the stuff that's in both, right? In order to plug a number into here, it has to be in the domain of both of those functions. And that's true whether you're trying to add the outputs, subtract the outputs, or multiply the outputs. Down here, things are a little more complicated. Certainly the same thing is true. If I'm going to plug x equals 2 in here. That means I'm plugging x equals 2 into f and x equals 2 into g. Both of those things need to be defined. So the domain of this function, f over g, is going to have something to do with this intersection, right? You have to be in that intersection to be in the domain here. But in addition to that, we need g to not be 0. So the domain of this guy, same as above, it's the intersection of the domains of f and g. But then we have to throw something away. And the symbol for that in set theory is a backslash. This is called a set minus. We're going to take the intersection of the domains, and then we're going to throw away any x's that make the bottom 0. Right? We cannot divide by 0, and here g of x is on the bottom of this fraction. So the domain of this expression is everything you can plug into f and g, right? Everything that you're able to plug into both, that's this stuff. But then you have to throw away anything that makes the bottom 0. So we have to throw away anything that makes the bottom 0. The domain for this last guy is more complicated. And generally, you'll find anytime you're asked to find the domain of some combination of two functions, you'll just follow the normal rules. You'll write down the expression, whatever that is, and then look for red flags. But what can we say about this? Well, if I'm going to plug an x in here, that means I have to be able to plug that x into the function g, and then take that output and plug it into the function f. So the kind of easiest thing we can say is that it must be a subset of the domain of g. All right, if I'm going to plug some number x in here, that means I'm going to plug that number into g, and then take that thing and plug that into f. So the first step is to plug into g. So the only way you can plug a number into this is if you can first plug it into g. And there might be deeper restrictions that come after that, but certainly you got to be able to get started, and that means you got to be able to plug into g. So these are the kind of new functions you can create out of a pair of functions. I think the best place to start after just seeing these definitions is to get a little bit of practice working with the definitions. And I have an example in mind for that. I'll hold here just for a second in case anybody's still writing. Maybe I'll refill my coffee. Okay. So given the graphs of f and g that I'm about to draw, we are going to calculate some outputs from those combined functions. Okay. So this is -1, this is 1, all is 2, all is 3, oops, -2, all 3, this is 0, comma, -2. Alright, so here's the graph y equals f of x. I'll draw over here. What's there? So the things I'd like to calculate, let's find f plus g of 0. Let's find f times g of 1. Or let's do 2. We can find f over g. Well, couldn't do that. Couldn't do that. Tell you what, let's find g over f of 2. Or how about negative 2? Yeah. And then f circ g of yeah, we'll do f circ g of positive 2, 1. Oh, we can do 1, and then g circ f of negative 2. All right. So we've got the graph of f, we've got the graph here of g, and we want to find all these things. I'll go one at a time. So how do I find f plus g of 0? Let's start with this guy. Any idea how I could get started there?
First, you would look at the graphs and find when x is 0.
Yeah, and so we need to look at both graphs where x is equal to 0. In other words, and I recommend always writing down this step, just write out what the definition says. So f plus g of 0, it's whatever it is, it's got to be f of 0 plus g of 0, because that's how this function is defined. And then each one of those on their own tells us to look at these individual graphs where x is equal to 0. So what is f of 0? Yeah, perfect, Suzanne, negative 2. And what is g of 0? Good, 0, right? When x is 0 on this graph, the output, the y value, g of x, is also 0. So g of 0 is 0. So this is negative 2 plus 0, which is negative 2. All right, that's the vibe. Nothing crazy. So what about finding f times g of 2? What would be kind of my first step, but here?
F of 2 times g of 2.
Yeah, f of 2 times g of 2. All right, no, you're good. So then looking at each graph, f of 2 looks like that's 3, and g of 2 looks like that's 0. So this would be 3 times 0, which is, oh, not 2, Jesus Christ, John, which is 0. All right, what about g over f of negative 2? Well, we begin the same way. You got to write out the definition. That's g of negative 2 divided by f of negative 2. F of negative 2 is positive 3, so the downstairs here is 3. G of negative 2, if we come on the graph of g over here, that's 0. 0 again. So this is 0 divided by 3. What is that? Good, 0. Yeah, if the 0 had shown up downstairs, that would be a problem. This would be undefined. But a 0 upstairs is no problem. All right, the composite functions are more interesting. So if I want to find f circ g of 1, just like all of these, we had to start by writing down the definition. You really want to start by writing down the definition here. This is f of g of 1. Alright, that's the definition. F circ g of anything is f of g of that thing. And then we have to look on the graph of g. You got to find the inside piece first, right? And I know it's a little bit misleading, right? Because in English we read from left to right, so it kind of looks like f is happening first, but it's not. It's not. This is f of g of 1. So you got to find g of 1 first. You got to find this inside piece, then you know what you're plugging into f. So, okay, what is g of 1? Well, g of 1, look on the graph of g, come up here to 1, g of 1 is 1. Didn't have to be, but it is. So f of g of 1 is f of 1, because g of 1 is 1. Now if I look on the graph of f of 1, that's 0. So this is 0. Didn't plan for all these to come out at 0, just happened that way. Alright, we got one more. That's g circ f of negative 2. Well, that would be g of f of negative 2. Alright, so we're doing the composition in the different order. So the inner thing that I need to figure out is f of negative 2. So I look on the graph of f. When x is negative 2, we're up here at 3. So f of negative 2 is 3. Alright, that means g of f of negative 2 is g of 3. And then I look on the graph of g. What is g of 3? Well, okay, here's 3. The y value down there is negative 1, so g of 3 is negative 1. And that means g circ f of negative 2 is negative 1. Any questions about any of these guys?
I have a question. So if like A was on the test, would we just write negative 2 or would we need to write it a certain way?
Good question. Free response question. I'd want to see you calculating, or at least showing me what these are. So definitely show your work. Whatever your process is to find things, write it down. Certainly true, false, or free response, or true, false, or multiple choice question, there's no issue of that. But I would like to see you at least telling me what these are individually. But on a test question, I'll be crafting those questions pretty carefully. So they will be, the free response questions, there will be ones for which you must show work. I'll put really clearly in the instructions the level of work I'm expecting you to show. Fair question. Any other questions on this? Okay. So we can do all this stuff graphically. We can compute outputs from these things one at a time using graphs. Another thing you want to practice is finding these combinations and their domains algebraically. So let's find f plus g, f times g, f over g, and f circ g, and their domains. Where f of x is something like x over x plus 1, and g of x is not a lot of numbers like that, are there? Yeah, we'll just do it like this. That's fine. So I want to find each of these new functions and their domains, given this is f and this is g. I think it's nice to write down the domain of f and the domain of g at the start, and then we can kind of compare the claim I made at the start of class with the results we find. So the domain of f here, there's only one like red flag. It's this x plus 1 in the denominator. I know that's not allowed to be 0, so x has to stay away from -1, which means his domain is -infinity to -1 unioned with -1 to infinity. The domain of g, this guy doesn't have any red flags. His domain is all real numbers. What is the intersection of those two sets? If I intersect this with this, what do I get? Between the sets all real numbers and all real numbers except -1, what is common to both? Is 2 in the intersection? If I intersect these, I just look at the overlap. Is the number 2 in there? Well, is 2 in the first set? Is the number 2 an element of this set?
Yes.
It is. Yeah, this is everything except -1. 2 is definitely in there. Is 2 in this set?
Yes.
Yes, it is. So is 2 in the overlap, the intersection? It's in this, it's in this. Does that mean it's in the intersection? It does. That's what intersection means. It's the stuff that's common to both sets. The intersection here is actually the same as this set. Right? The only number that's not in this set is -1. That's the only thing from here that's not here, and everything that's here is here. So the overlap is exactly this. So I claim that f plus g and f times g will both have this as their domains. Right? That's from the rule that we showed at the start of the class when we defined these things. Let's take a look. So the good news is you don't need to do those set operations to find these domains. You just need to follow the normal rules. You write down the thing and then look for red flags. So f plus g of x is f of x plus g of x. F of x is x over x plus 1. G of x is 1 minus x squared. And I do recommend putting these usually in parentheses, at least to start, and then ask yourself, do I need the parens? Oh yeah, very good, Suzanne. I'm sorry, I didn't see your answer in chat earlier. And then we can ask ourselves, what do I need to do to find this domain? So this guy, the parentheses really aren't doing anything, x over x plus 1 plus, and over here the parens really aren't doing anything either. I could put these together into a common denominator, single fraction, but I don't need to do that to find the domain. I just look for red flags. So this guy, no red flags. This guy, just the one red flag coming from this stuff downstairs. We know that x plus 1 is not allowed to be 0, so x is not allowed to be -1, i.e. the domain here is -infinity to -1, unioned with -1 to infinity. All right, in other words, the way that we mashed these two functions together didn't create any new domain red flags. That's not always going to be the case, but we said that would be the case for f plus g, f minus g, and f times g. And here that matches with what we said earlier. Okay, f times g. Well, f times g of x is f of x times g of x, which is x over x plus 1 times 1 minus x squared. There is stuff I can do here, and in fact it's possible to get into some trouble with this, so I want to take a second here and let's go ahead and multiply these. So that would be x times 1 minus x squared divided by x plus 1, which I'll write in parentheses like that. And then the 1 minus x squared can be factored. This is x times 1 minus x times 1 plus x, all divided by x plus 1. And 1 plus x is the same as x plus 1. You can cancel those, and you get x times 1 minus x. However, you can only cancel those if the factor you're canceling is non-zero. Right? 0 over 0 is not 1. You cannot cancel 0 over 0 and call that 1. Anytime you have a 0 downstairs, the object is undefined. So this expression is equal to this expression, but only for x values for which this expression is defined. And this is not defined when x is equal to negative 1, i.e. if x plus 1 is not equal to 0. When I say you can get in trouble finding domains, this is what I mean. It's a very natural process to write these down, factor, cancel, and get this, and then look at this and say, oh, there's no domain restriction here. This doesn't have any red flags. The domain is all real numbers. But this is only equal to this if you stay away from negative 1. So here's a rule. Every time you cancel a factor top to bottom, make this little note. As long as you do that, you won't get into trouble here. But if you fail to do that, and you choose to try to find your domain from this fully simplified factored and canceled version, you will get into trouble. The way I normally tell students to avoid this is to stop at one of these steps. In fact, just stop right here to find the domain. So when you're trying to find the domain of some combination of functions, write the fucking thing down. Don't simplify anything at all. Stop and find the domain right away. So when I look at this, what red flags are there? Well, this doesn't have any. This is not a problem. Oh, but this is. So again, the red flag comes from x plus 1. Not allowed to be 0. So x is not allowed to be negative 1. And your domain is what it should be, negative infinity to negative 1, unioned with negative 1 to infinity. But if you proceed to combine, factor, and cancel, and then you only look at this to find your domain, you're going to think that the domain is all real numbers. I'm trying to head off the many, many emails I'm going to get from this section, because I always get many questions related to this sort of thing. So when you're trying to find the domain of a combination of functions, write the thing down, and then stop. Find the domain there. Then simplify. Right? It is nice to simplify. And if you insist on going through this process right away, which is not unreasonable, anytime you cancel a factor, make sure you take note of the x values for which that cancellation is valid. That cancellation is not valid for any x value that makes the factor you're canceling equal 0. So here the factor I'm canceling is x plus 1. That's a totally okay thing to do, as long as x plus 1 is not 0. If x plus 1 is 0, then this is 0, this is 0. You got 0 over 0. You cannot cancel 0 over 0 and call that 1. All right, if you plug -1 in here, you get -1 times +2 times 0. And downstairs, you just have 0. That's 0 over 0. That is not 1. Those do not cancel. But for any other number, any other value of x besides -1, those do cancel, and you get this. So as long as you remember this, then you could also just go right here. Okay, so the domain doesn't include -1, and you're Gucci. But if you find yourself getting into trouble, if you're nervous about this, the rule is write the thing down, find the domain before you simplify anything, then go ahead and simplify. All right, let's finish up. We want to find f over g. So f over g of x, we know that is f of x divided by g of x, which is x over x plus 1 divided by 1 minus x squared. Same sort of thing, right? Stop at this step and find the domain. So what sort of red flags do we have? Well, I've got this little fraction upstairs, and that little fraction has an x plus 1 downstairs. So I know x plus 1 is not allowed to be 0, which means x is not allowed to be -1. And then I also have this piece downstairs. Which is not allowed to be 0. And the x values that would make that 0 are any x values that have a square equal to 1. When you take square roots on both sides here, you get plus and minus the square root of 1 equals x squared, i.e. plus and minus 1. Sorry, equals x. Equals x. So from this piece, I know x isn't allowed to be -1. And from this piece, I know x isn't allowed to be positive or -1. So the domain for this guy is a little bit different. It's everything except for positive or -1. That's -infinity to -1, union with -1 to +1, union with +1 to infinity. This guy said x is not allowed to be -1. This guy said x is not allowed to be positive or -1. So I've got to kick -1 out, and I've got to kick positive and -1 out. Well, that means I'm kicking positive and -1 out. So that's everything except plus or minus 1, which is this. Questions on these first three before we do the composite? Okay. Let's look at that composite function. F circ G is, by definition, f of g of x. And there's more than one way to do this, but my recommendation is to say work from the inside out. Right? That's generally what we do, and it makes sense to do that. So this is f of g of x, which is f of something. What is g of x? Well, g of x is 1 minus x squared. And this is just like that stuff from your very first or maybe second homework, right? Where you had to compute f of 1 over x, f of a plus h, f of 1 minus x, all that stuff. This is exactly one of those things. So how do you find this? What is f of 1 minus x squared?
in 1 minus x squared into x over x plus 1?
I think I maybe heard some of it, but I heard an x plus 1, which isn't quite correct. So f of x is x over x plus 1, which means like f of a would be a over a plus 1. F of some shit would be that shit divided by that shit plus 1. And I can be even more crude if we need to. F of your mom would be your mom divided by your mom plus 1. So like f of anything is that thing divided by that thing plus 1. Which means f of 1 minus x squared is 1 minus x squared divided by 1 minus x squared plus 1. And we should put these in parentheses. So remember, anytime you're plugging in to a function, right, you can plug whatever you want in here. You can plug dog shit in here. It would be dog shit over dog shit plus 1. We can plug the function g of x in there. And since g of x is 1 minus x squared, that's 1 minus x squared over 1 minus x squared plus 1. Can I cancel the 1 minus x squared here? Do those cancel? Very good. Yeah, Suzanne's got it in the chat there. That's a no. Why not? Well, it's like saying, can I cancel the x's here, right? In x over x plus 1. No, because x is not a factor of the bottom. In fact, if you want to, and since we're going to have to anyway, we can find the factors of the top and the bottom. The top is, I'll just leave it as 1 minus x squared for now. Downstairs, 1 minus x squared plus 1 is 2 minus x squared. And there's a neat factoring trick called the difference of squares. Says a squared minus b squared, any expression of that form can always be written as a minus b times a plus b. Yeah, perfect, Suzanne. Right, yeah, there's not a 1 minus x squared factor specifically right here, so I can't pull a copy out. So if you want to know if you can cancel something, the very first thing you should do is combine all the like terms and factor. And then, if you have a factor of the top that is the same as a factor of the bottom, then and only then can you cancel. So I can use this factoring trick on both the top and the bottom here. 1 minus x squared factors as 1 minus x times 1 plus x. Here a is 1, b is x. And downstairs, 2 is not a perfect square, but it is the square of something. It's the square of the square root of 2. So that's how the bottom factors. And you see that there are no common factors. There is no factor upstairs that is also downstairs. So there's nothing that can be canceled here. But this does tell me how to find the domain. The domain is going to be everything except for the numbers that make these pieces 0. And what makes these pieces 0? Well, this guy is 0 if x is equal to root 2. And this guy is 0 if x is equal to negative root 2. So the domain here, we know that root 2 minus x times root 2 plus x has to be non-zero. And for this guy, that tells me x can't be the square root of 2. This guy tells me x can't be the negative square root of 2. And you could get that from here also, right? If you set this downstairs equal to 0 and then solve by taking square roots, you'll get plus and minus the square root of 2. So our domain is negative infinity to negative root 2, union with negative root 2 to positive root 2, union with positive root 2 to positive infinity. Okay. Questions here? A little quiet today. Okay. So, all of these other combinations of functions, the sum, the difference, the product, the quotient, they're not horribly exciting. But the composite function, there's a neat way to conceptualize those. And it gives me an excuse to remind you of machine diagrams. So I'm going to say recall a function can be understood as a machine diagram. Maybe it can be understood, I should say, it can be conceptualized as a machine diagram. What do I mean by that? Well, I mean, you can think of your function as like a little machine on an assembly line. There's stuff that comes in here, and there's stuff that comes out here. If you send in an x, the f machine will send out f of x. And maybe it's the machine that adds 3, right? So you send in x equals 5, it sends out 8. You send in 7, it sends out 10. Or maybe f is the squaring machine, right? You send in 2, it sends out 4. You send in 3, it sends out 9. F could be any sort of machine. The idea is it has an input and an output. This way of thinking about things is really useful when it comes to sort of understanding what the composite function does. In this scheme, the composite f circ g is the, and I know this is a little gross, but you can think of it as like the human centipede of machine diagrams. And what I mean by that is you take the output from one and stitch it up to the input from another. And when you do that, this is what you get. So I've got my G machine here. X's come in, and G of X's go out. And then I connect that to my F machine. So the F machine normally takes in X's and spits out F of X's. If you were to take in G of X's, then it would spit out F of that, which is F of G of X. And this whole thing together is the machine diagram for F circ G. That's what we're looking at here. So if you have a complicated process that can be broken down into simpler processes, one done after the next, this can be a really useful way to understand those complicated processes. Like maybe I've got some function, it takes your number, it squares that number, it adds 1, and then takes the square root. That would be like the square root of x squared plus 1. maybe g there would be the squaring plus 1 function, and then f would be the square root function. And the whole thing together would be the square root of x squared plus 1. Turns out to be a really useful way to think about functions, right? Very, very useful. It kind of leads us to an interesting question. If these two functions were to exactly undo one another, what would come out over here? Or what does it mean for two functions to exactly undo one another? This is kind of the big question on which we're going to end for today. We might be a little early. Yeah, a little early. We're going to end a little early today. That's okay. So, question. Given a function f, is it possible to find another function which undoes whatever it is that f does? In other words, can I take this machine and run it backwards? Is that possible? And if so, what would it look like? The answer here is a little bit subtle. So it kind of depends on how the function f works. It's possible for a function to kind of destroy the information that you would need to run it backwards. The example I like here is, imagine at a recycling plant, you've got a machine that takes in a soda can and it just burns off all the paint. That's what it does. The function that undoes that would take each soda can, each blank soda can, and repaint it with the paint that it originally had. So, original machine takes the Coke can in and it burns the Coke logo off and spits out a clean silver blank can. If you've got that pile of clean silver blank cans and you want to exactly undo the process that led to them, you would need to repaint each one with the logo it originally had. But because it's a pile of blank fucking cans, you don't know which one was a Coke can, which one was a Pepsi can, which one was a Sprite can, whatever. If the original function destroys the information of the input when it sends that input to an output, then you can't undo that function. There's no way for me to undo the paint burning off machine because I don't know which can to paint with the Coke logo and which can to paint with the Fanta logo or whatever. So the answer here is yes, but only under certain conditions. In the example with the soda machine, here's one way to think of it. What if my burn the logo off machine, in addition to scorching off the paint, stamped each can with something, some little like imprint that said Coke, Pepsi, Fanta, Sprite, whatever. Then you could look at your pile of blank cans and say, okay, this one needs to get painted with that logo, this one needs to get painted with that logo. So if the original function somehow preserves the information, you can look at each output, the blank can, and tell from which input it came, then and only then can you undo that function. This is called being a one-to-one mapping, or a one-to-one function. Each input needs to go to a distinct output. If every input goes to his own output, then I can send each of those outputs back to the input from which it came. That's running the machine backwards. If every input goes to the same output, like in the soda example, where every, Coke, Pepsi, Sprite, whatever, all get mapped to a blank can, then I don't know how to send that backwards. I don't know how to undo that process, because I don't know which output should go back to each input. So if your function preserves the information of the input in the output, then you can run it backwards. I think that's enough to dump on you for one day. You've got a homework set up, and there's going to be another one up just a little bit later. So right now you have you have this homework, right? Homework 6 that you're working on, rather than having that be due today, I set that to be due on Monday for you guys, or Tuesday, whatever our next class period is, after this one. In addition to that, you're going to have another homework 7, that I'm going to open up here in just a few minutes, and that will be the last part of section 2.7. That will also be due on the first day of class next week, next Tuesday. And then remember, next Thursday is going to be our first test, and it's going to cover sections 1.1 through 2.8. Next Tuesday we'll learn about 2.8, which is this whole inverse function thing. How do you run the machine backwards? To talk about that, we'll need to be clear about what those conditions are, right, being a one-to-one function. But that's it. Then we're ready for the test. So the test will be next Thursday. If you have anything you need, you can talk to me. You're worried about something, you want to work problems, anything like that, just send me a Canvas message or pop into the Discord or come see me in office hours. I have an office hour tomorrow from 1 to 2 p.m. Otherwise, I will see you guys next Tuesday. Take care.